Today we're looking at using matrices to solve equations involving 2 by 2 matrices. So in terms of matrix equations, if we have matrix A being multiplied by some unknown matrix X, and we're told that that product is equal to B, if we want to get X on its own, then we need to take the inverse of A, multiply it by A and X. Then of course, whatever we do to the left-hand side of the equation, we also have to do to the right-hand side. So we get the following. Now, the order of this is very important. Whatever order that we do it on the left-hand side has to be done on the right-hand side, and we'll see that with part 2 here. So if you have anything and its inverse being multiplied together, that becomes the identity matrix. So the identity matrix times X is equal to the inverse of A times B. We have this property with the identity matrix, which is that anything times the identity matrix is itself. So that is how we would solve for the unknown if A is being multiplied by X from the left-hand side. If it's from the right-hand side, we need to multiply it by the inverse on the right-hand side. So doing that, we get a similar solution where X is equal to B times A inverse. So let's see in this in practice. So we've got A equals 3, 5, negative 4, negative 6. What I first want to do is determine what is my A inverse. So, reminder, that's 1 over AD take BC times, if it was ABCD, we want it to be D, negative B, negative C, A. So the main diagonal swaps and the off diagonal becomes negative. And so in this case, that's going to become 1 over 3 times negative 6 is negative 18. 5 times negative 4 is negative 20, but we're subtracting it, so it's plus 20. And then that gives us negative 6, positive 4, negative 5, 3. So that's the inverse of A. We can solve the determinant, which is the denominator of that fraction there, and we get the following. So now that we have this matrix A, we want to solve, this inverse of the matrix A, we want to solve the equation that we've been given. So, part A, we want to get X on its own. So the way we do that is multiply by A inverse on the left-hand side. And so we get identity times X is equal to A inverse times C. And so X is just A inverse times C. So we're going to get here a half of negative 6, 4, negative 5, 3, multiplied by negative 1, 2. So in doing so, we can either apply this a half at this stage, or we can multiply this through and then apply this half. Both will give the same solution. It's easier to work with whole numbers, so I'll apply this half at the final stage. So a 2 by 2 multiplied by a 2 by 1 is going to give us a 2 by 1 matrix. So we get negative 6 times negative 1 is 6, plus 8 is 14. And then we also get positive 5 times 6 is going to give us, plus 6 is going to give us 11. So our final solution will be 14 on 2, 11 on 2. Okay, back up to part B. We now want to multiply from the right-hand side. So multiplying by A inverse on the right, we get X times I is equal to D A inverse. And so X is equal to D times A inverse. So that will give us 3 and negative 2 multiplied by negative 6, 4, negative 5, 3. And then, of course, I'm going to take that half out the front. So whatever the product of these two matrices is, I'm going to halve each component of it. So I've got a 1 by 2 multiplied by a 2 by 2. So I'm going to end up with a 1 by 2. So we get 3 times negative 6 is negative 18, plus 10 is going to give me negative 8. We then get 12 minus 6 is going to be 6. So that will give me negative 4, 3. we can apply this idea to simultaneous equations. So you'll notice that this is 4 times x plus 5 times y equals 6. So if we were to write that in terms of rows and columns of a matrix, we could have 4, 5 in one, and then x, y in another. And so if we also apply this to our second, we get 3, 2, so 3 times x plus 2 times y, and we know that that is going to be equal to 6, 8. So what we can do is let this equal ax is equal to b. So let a equal this matrix, let x equal this matrix, let b equal this matrix, and we need to find x on its own. So we've got a inverse times a times x is equal to a inverse times b. So we get ix is equal to a inverse times b, which means x is equal to a inverse times b. So what is a inverse? Let's find that out. So we've got 1 over 8 take 15. So that's going to be -7 there. We swap our main diagonal, 2 and 4. We turn our off diagonal to negative, and so a inverse equals 1, -1 on 7, 2, -5, -3, and 4. And so again, we're not going to apply this coefficient until the very end, because that's going to make it easier for us. So x is equal to -1/7, 2, -5, -3, 4, multiplied by 6, 8. Just like we discovered here, we need to be multiplying it from the left. So 2 by 2 matrix times 2 by 1 matrix is going to give me a 2 by 1 matrix. So it's 1/7. We've got 12 minus 40. So 12 minus 40 will give me -28. And then -18 plus 32 is going to give me +14. So my answer to this is going to be -1/7 times 28, so that's +4, and -2. So if we substitute x equals 4 and y equals -2 back into our original two equations, we should get 6 and 8. So you'll notice, in order to do this, it all hinges on the fact that this inverse exists. So if the determinant of A is non-zero, then there is a solution to these simultaneous equations. If the determinant is equal to 0, then either there is no solution or there is an infinite number of solutions. So in terms of graphically what that means, just a reminder, simultaneous equations are finding the intersection of two lines. So if there's an infinite number of solutions, that means line 1 is the same as line 2. And if there's no solutions, that means line 1 is parallel to line 2. So we can see that there. That's all for this episode. Thank you very much for watching.